All right, let's jump right in. Today, we are tackling a topic that looks, I know, super intimidating, but it's actually one of the most powerful tools you can have in math, the binomial theorem. So forget the scary-looking formulas for a second and think of this as your new secret weapon for algebra.
So, here's our game plan. We're going to build your binomial theorem toolkit right from the ground up. First, we'll get the master key, the main formula. Then, we'll grab some precision tools that let you find specific little pieces of the expansion. After that, we'll figure out how to find the single biggest, most powerful term, uncover some really cool hidden patterns, and then finally, we'll level up and see how to use this for any kind of power.
So let's just start with the challenge, right? Imagine your teacher asks you to expand this, x plus a, to the power of 100. I mean, could you do it by hand? Sure, but it would be an absolute nightmare. You'd be there forever. Well, that's exactly the kind of problem the binomial theorem just solves beautifully.
Okay, so it's time to get our hands on that master key. This is the core idea, the one thing that's going to unlock everything else we talk about today.
And here it is. This is the binomial theorem. Now, don't let all the letters and numbers freak you out. It's really just a recipe. Those NCR parts, they're just the numbers out front of each term. It's a notation that means n choose r, and it just tells you how many ways you can pick r things from a set of n. And look at the pattern. The power of x starts at n and drops with each term, while the power of a starts at 0 and climbs up. That perfect symmetry, that's the real magic here.
Now this little guy here, the general term, is a massive shortcut. Seriously, instead of writing out all 101 terms of our x plus a to the 100 problem, what if you only needed, say, the fifth term? Well, this formula, t sub r plus 1, lets you jump right to it. It is an absolute game changer for exams.
Okay, so we've got the master key. Now let's grab some of those more specialized precision tools. Because sometimes you don't really care if it's the 5th or 10th term. You care about the term that has a very specific power of x.
Exactly. Like what if the question asks for the term that has x to the power of 7? Or what about the constant term? The one that has no x in it at all. These are super common questions, and our next tool is built just for them.
And the process is so simple, it's just 3 steps, every time. First, you just write down that general term formula we just looked at. Step 2, you grab the part of the formula with the power of x and you just set it equal to whatever power you're looking for, maybe 7. And finally, step 3, you solve that little equation for r. That's it. Once you have r, you plug it back in and boom, you've got your term. It's totally systematic.
Okay, but what about another classic question? Finding the term that's sitting smack dab in the middle of the whole expansion. But wait, is there always just one middle term?
Well, as you can see, it really depends on your main power, n. See, if n is an even number, like 10, you get an odd number of terms in total. So there's one single clear middle term, and you find it with that formula, n over 2 plus 1. But if n is an odd number, like 9, you actually get an even number of terms. So you have 2 terms sharing that middle spot, and you find them with those 2 formulas right there. It's simple, but you got to know which case you're dealing with.
All right, tool number 3. We found a specific term, we found the middle term, but what if we want to find the single biggest term of the whole bunch? The one with the largest numerical value.
Let's make it concrete. Imagine you have an expansion like 1 plus 4x to the 8th power. And let's say we give x a value, maybe x is 1/2. One of those 9 terms is going to be bigger than all the others. The values kind of rise up and then fall back down. We're trying to find the very peak of that mountain.
And this formula is the machine that finds it. It looks a little intense, I know, but it's just a way to find the right value of r. This is super useful in things like probability, where you might want to find the most likely outcome. All you do is plug in your n, your x, and your a values, solve for r, and it points you straight to the greatest term in the series. It's a powerful way to find that peak without calculating everything.
Now for what I think is the coolest part. Those numbers in front of each term, the binomial coefficients, they aren't just random. Nope, they are hiding some truly beautiful and surprisingly simple patterns. Let's go and cover some.
Think about this for a second. What happens if you just add up all of those coefficients? For any power n, you take the first coefficient, add the second, add the third, all the way to the end. What do you think you get?
Boom! It's just 2 to the power of n. That's it. So for an expansion to the 10th power, the sum of all 11 coefficients is just 2 to the 10th, or 1024. This thing that looks super complicated simplifies to something so clean and elegant, it's amazing.
Okay, how about another one? What if we alternate the signs? So we add the first one, subtract the second, add the third, minus the fourth, and so on. Incredibly, the result is always 0. It's just another one of those beautiful little shortcuts hidden right inside the theorem.
So you can think of this slide as your personal cheat sheet for coefficients. Now, don't feel like you have to memorize all of this right now. The big takeaway is that these relationships are your secret weapons for solving problems fast, especially if you're in a timed exam. All right, time to level up. Everything we've done so far has been with n as a nice positive whole number. But what if the power is negative, or what if it's a fraction? Well, turns out the theorem can handle that too.
And here is the single most important difference you need to understand. When n is a positive integer, the expansion eventually stops. It's finite. But when n is negative, or a fraction, the expansion goes on forever. It becomes an infinite series. And this is so important because it's the key to making really accurate approximations in physics and engineering.
And this is the formula that makes it all work. It looks pretty similar to our original one, right? But it's been adapted so it works for any power. This is what lets us expand something like 1 minus x to the power of -1, and it turns into this beautiful infinite pattern. 1 plus x squared plus x cubed, and on and on. It's an incredibly powerful link to the world of infinite series.
So, as we've seen, the binomial theorem is way more than just a formula. It's a key. It's a tool for finding specific parts of a puzzle, for finding the highest peak, and for seeing these deep, hidden patterns in numbers. It shows up everywhere: probability, statistics, even finance. So the real question isn't what we've unlocked today, but now that you have the toolkit, what other patterns are you going to unlock with it?